Welcome to today's paper reading. Today's paper is titled, Warm, on the Benefits of Weight Average Reward Models. This paper was published on the AR14 preprint by Alexandre Ramé and colleagues from Google DeepMind. Warm introduces a scalable approximation to traditional ensembling methods, enhancing reliability and robustness. The key contributions include innovative reward modeling, theoretical and empirical insights into weight averaging, and experimental validation demonstrating performance improvements and mitigated reward hacking, achieving a high win rate of 79.4%. Figure 1a demonstrates the alignment process using weight average reward models, WARM. Starting from a supervised fine-tuned, SFT, large language model, LLM, reinforcement learning, RL, fine-tuning is applied to optimize a proxy reward model, RM, consistent with reinforcement learning from human feedback, RLHF. The key innovation of WARM is the proxy RM, which is the weight average, WA, of individual RMs, each fine-tuned from a shared pre-trained LLM on the same preference dataset but with diverse hyperparameters. This WA approach is efficient and enhances reliability under distribution shifts and robustness under inconsistent preferences. Figure 1b illustrates the impact during RL alignment. The control reward initially increases but eventually deteriorates, a phenomenon known as reward hacking. However, when WARM is used as the proxy RM, increasing significantly improves absolute results while delaying the collapse, as indicated by the control rewards maintaining higher values for longer during training. Figure 2 illustrates the baklava diversity procedure, which starts with a pre-trained large language model, LLM, theta. Different checkpoints, theta, equals 1 are collected along a single supervised fine-tuning, SFT, run at various training steps. These checkpoints are used to initialize multiple reward model, RM, fine-tunings on a preference dataset, leading to the learning of phi equals 1. Finally, these RMs are weight averaged to form the final model phi WRM. Figure 3 presents experiments under distribution shifts, validating observations 1 and 2 on the TLDR summarization benchmark. The accuracies on D are reported when interpolating between two RM weights phi1 and phi2 with the coefficient lambda sliding between 0 and 1. Weight averaging, WA, is represented by 1 minus lambda, phi1 plus lambda phi2, while ensembling, ENS, combines the predictions, 1 minus lambda, times phi1 plus lambda times phi2. The diagonal, diagram, represents the interpolated accuracy, 1 minus lambda, times ACC SID 0, phi 1, SID 1, plus lambda times ACC SID 0, phi 2, SID 1. The figure explores increasing diversity between phi 1 and phi 2, including different training steps, data order, learning rates, and SFT checkpoints. Figure 4 presents a corruption experiment that validates observation 3. Two reward models, phi 1 and phi 2, are fine-tuned independently with 25% of the training labels corrupted. The performances of their weight averaging, WA, and ensembling, ENS, are reported across different data subsets. It is observed that WA reduces the memorization of corrupted labels, as shown in Figure 4a. However, WA still performs slightly worse than ENS on clean training samples, as depicted in Figure 4b. Interestingly, the performance of WA relative to ENS improves as the data moves away from the training distribution, particularly on the out-of-distribution, OD, dataset D in Figure 4d, where WA demonstrates better generalization capabilities. Figure 5 presents histograms illustrating the differences in accuracy between weight averaging, WA, and ensembling, ENS, across various data subsets. Notably, WA performs significantly worse than ENS on corrupted training data, indicating reduced memorization and improved robustness to label corruption. Conversely, WA is worse or equal to ENS on clean training data. On out-of-distribution test data, WA outperforms ENS, demonstrating better reliability under distribution shifts. These results suggest that weight averaging memorizes less and generalizes better than ensembling predictions. Figure 6 illustrates the control reward for best of N (BAN) experiments under clean and corrupted preference datasets. The x-axis represents the KL divergence between the bond policy and the SFT policy, while the y-axis shows the control reward gains compared to the best individual RM Phi1. The blue lines indicate warm with different numbers of weights, demonstrating that warm consistently achieves higher control rewards than individual RMs and ensembling methods, ENS. This performance is crucial for validating the effectiveness of warm in scenarios with varying degrees of label corruption and different SFT policies. Figure 7 presents the Oracle preference metric for best of bond experiments on T5 generations. The figure is divided into 4 subplots, 7a and 7c for the clean preference dataset, and 7b and 7d for the dataset with 25% label corruption. The win rates for various values of are plotted against 2 reference strategies, SFT, random selection, and the best summary selected by warm with equals 6. The results show that all strategies outperformed the SFT reference, maintaining win rates above 50%. However, none of the strategies surpassed the warm equals 6 reference, indicating its superior performance. Figure 8 illustrates the control reward for reinforcement learning (RL) experiments, focusing on the clean preference dataset in figures 8a and 8c, and the dataset with 25% corruptions in figure 8b. The blue lines represent the RL fine-tuning of policies using weight average reward models, WARM, with varying numbers of average reward models. The darker the blue line, the higher the value of. These WARM-based policies consistently outperform those fine-tuned with individual reward models, shown in yellow, and those that ensemble their predictions, shown in red. Specifically, WARM significantly improves absolute results and delays the collapse of control rewards, maintaining higher values for longer periods during training. In Figure 8c, the results of policies fine-tuned with WARM equals 6 or the best individual reward model, Phi1, are presented for different values of alpha, which controls the Kullback-Leibler, KL, regularization strength. This figure highlights that WARM not only outperforms individual RMs but also performs better than prediction ensembling, ENS, methods in RL fine-tuning scenarios. Figure 9 presents the Oracle preference metric for reinforcement learning, RL, experiments using a clean preference dataset. The win rates are plotted against 3 reference policies: the supervised fine-tuning, SFT, policy, the policy fine-tuned with WARM equals 6 after 3,500 steps, and the policy fine-tuned with Phi1 after 3,000 steps. The results show that the policy fine-tuned with WARM equals 6 achieves the highest win rate of 99.8% after 3,500 steps, outperforming all other policies. Additionally, policies trained with WARM, even with equals 2, demonstrate superior performance compared to the Phi1 policy, indicating the effectiveness of WARM in improving RL fine-tuning outcomes. This introduction focuses on the advancements in large language models, particularly in the area of reward modeling. The authors discussed the challenges faced during fine-tuning, such as distortions in pre-trained features and underperformance out of distribution. They also highlight the benefits of weight averaging, which leads to wider optima and better generalization, as well as improved model selection. Additionally, the section touches on the importance of adversarial robustness, emphasizing the need for local Lipschitzness, certified robustness, and new neural network smoothness constraints. The methodology of this study focuses on leveraging weight averaging, WA, techniques to enhance the robustness and reliability of reward models, RM. WA methods have been shown to improve model robustness by flattening the loss landscape and reducing variance, which is crucial for handling model misspecification. In the context of reward modeling, WA helps in aligning large language models, LLMs, by providing a more stable and accurate reward signal, which is essential for tasks involving human preferences. The experimental setup includes the use of the Reddit TLDR dataset for summarization tasks, where AI labeling is performed using an instruct fine-tuned PAL-ML model. The reward models are based on PAL-MXXS architectures, which are pre-trained and then fine-tuned on the dataset. This approach ensures that the models are capable of handling label corruption and improving overall model performance. Figure 10 analyzes the weight selection procedure by plotting the accuracy resulting from averaging weights out of 10, where the weights are chosen based on various selection procedures. The procedures include selecting from best to worst, first best and then random permutation V1, random permutation V2, and from worst to best. The analysis effectively validates that choosing models from best to worst serves as a reliable heuristic for improving accuracy. Figure 11 presents additional results that enrich the data shown in Figure 4, specifically focusing on the train, corrupt, scenario. This figure aims to provide a more comprehensive view of the experimental outcomes under corrupted training conditions, thereby enhancing the understanding of the robustness and effectiveness of the weight averaging method in ensemble models. Figure 12 presents additional results for the trained data, enhancing the information provided in Figure 4. These results are derived from clean data processing, ensuring accuracy and reliability. The comparison with Figure 4 highlights the improvements and additional insights gained from the enriched data set. Figure 13 presents additional validation results that enrich the data presented in Figure 4. These results specifically pertain to the validation of different pairs of RMs as shown in Figure 4b. The data in Figure 13 is ID-specific, providing more detailed insights into the validation process. Figure 14 presents additional results from out-of-distribution (OD) testing, which serve to enrich the findings presented in Figure 4. These results are derived from testing with different pairs of RMs, providing a more comprehensive view of the performance and robustness of the system under varying conditions. Figure 16 presents the control-reward for Bond experiments under a clean setup, specifically focusing on the baklava scenario. The figure highlights the impact of different featurizer initializations for the two fine-tunings, Phi1 and Phi3, which were collected at 12,000 and 8,000 steps respectively from a shared supervised fine-tuning, SFT. This setup allows for a detailed comparison of the control reward across these conditions, providing insights into the performance and stability of the models under different initialization strategies. Figure 17 presents the Oracle preference metric for Bond experiments under a clean setup. Subfigure A verifies the findings from Figure 7c, but applied to generations from the Palm SFT. Subfigure B illustrates the win rates for Bond on T5 generations when using warm with equals 6 and a fixed equals 1000, compared against other reward models, RMs, where 1 less than or equal to 1000. This figure validates that Bond effectively limits reward hacking compared to reinforcement learning, RL, as performance improves with increasing. In the experiments, the authors evaluated the performance of the weight average reward models, WARM, under two conditions, with a corrupted preference dataset and with a clean preference dataset. For the corrupted dataset, they introduced a 25% corruption rate and analyzed the win ratio against WARM with M equals 6 and the control reward. In the clean dataset experiments, they focused on the win rate of WARM M equals 6, the impact of the parameter alpha, and the Oracle preference metric. Both setups involved a fixed number of training steps, allowing for a direct comparison of policies. The out-of-distribution, OD, accuracy was also considered, particularly in relation to the best single reward model, RM Phi1. Figure 19a presents the win rate of the policy fine-tuned with WARM equals 6 against other policies at the same number of training steps. This comparison highlights the effectiveness of WARM in maintaining a higher win rate across different training stages. Figure 19b illustrates how the win rate of WARM equals 6 varies against the policy trained with the best performing single RM Phi1, showing the influence of different KL regularization strengths alpha. This analysis underscores the importance of tuning alpha to achieve optimal performance in RL experiments. In the related work section, the focus is on the impact of the KL regularization strength, controlled by the parameter alpha. Different values of alpha have been explored in previous studies, each affecting model performance in various ways. These studies have shown that varying alpha can influence model stability and accuracy, highlighting the importance of finding an optimal value. The current research builds on this by conducting a comparative analysis to determine the most effective alpha, with implications for future research in this area. In this conclusion, we analyze the control reward in relation to training steps and KL divergence. For alpha equals 0.01, we observe the win ratio against warm models and the control reward over training steps. For alpha equals 0.001, we examine the control reward in relation to both training steps and KL divergence, comparing different warm models. Additionally, we discuss distillation experiments, where we reproduce the setup from 17, noting changes in diversity across fine-tuned reward models, which motivates our exploration of the more realistic RLHF setup. Figure 20 presents the control reward for reinforcement learning experiments conducted with a specific parameter alpha set to 0.01 under a clean setup. The graph illustrates the relationship between the control reward and the number of training steps, providing a comparative analysis of different models including warm and ENS. This visualization aids in understanding the performance and stability of these models across various training stages. Figure 21 presents the control reward for reinforcement learning (RL) experiments conducted under a clean setup with a learning rate parameter alpha set to 0.001. The figure illustrates the relationship between the control reward and the training steps, providing insights into the performance and stability of the RL models during the training process. This setup is crucial for understanding the impact of different learning rates on the control reward, which is a key metric in evaluating the effectiveness of RL algorithms. Figure 22 presents the Bond experiment within the distillation setup from 17. The control reward model, RM, provides the labels for the preference dataset, which is also used for the y-axis. The candidate summaries are generated using a supervised fine-tuning (SFT) model with the T5 architecture 111. The blue lines indicate the weighted aggregated reward model, WARM, with weights, demonstrating that WARM achieves higher performance compared to individual RMs, yellow lines, or when their predictions are ensembled, red line ENS. Thank you for watching.